Hello, our users. In this video, I want to show you how to do permutation test to compare distributions using R. First, a permutation test evaluates whether an observed difference could occur just by chance by repeatedly shuffling your actual data and recalculating the difference each time. If the observed differences is rare among these random shuffles, it's likely to be statistically meaningful. Okay, so what this says is you imagine if you have two distributions and they are the same, they're equal, then it doesn't matter how many times you shuffle the observation between the two samples because they are from the same distribution, so that will not create any deviations, right? So by doing a large number of shuffling, you created a variability, then you create a distribution of all these estimates based on shuffled data, okay? And then you compare the observed difference to this permutation distribution, and then you make a hypothesis test. Okay, that's the key idea of permutation test. Okay, but if you ask why do we need permutation test? Okay, so basically their strength is so for example, it does not require statistical assumptions like normal distributions or equal group sizes. Okay, and it works with any test statistic we care about, mean, median, differences in percent, etc. So because we assume the two distributions are the same, so any statistic you compute from distribution like even skewness, kurtosis, you can compare them using the permutation test. And also permutation test is robust to outliers and unusual data, which, the t-test may be very sensitive to outliers, but the permutation test is relatively robust. But permutation test is not without challenges. Okay, so first is really the computational intensive. So how many times shuffling you want to do, right? But fortunately, we have nowadays computing power, so it's very much doable until the design or the model become very complicated. Okay. Also, there's the underlying assumption of exchangeability of the distributions. Okay, and we're not sure. We assume it is, but it may not be. Okay, so. And also, still, small sample size may limit the accuracy of the permutation test. So even though you think it may have advantage for small sample size situation, but there's a limit to it. Okay. And also, permutation tests are, known to have problem with tied data points. Okay. If you have ties in the data, it may create problems for permutation tests. Okay. And permutations that really are not suitable for complex designs or models because when you really shuffle the two distributions, it's easy when you just have like IID sample from distributions. Okay, but if your model gets more complicated, like a permutation test for, I don't know, like a mixed facts model, and then things get a lot more complicated. So let me show you an example here. Is a compare means. Let's set up the random seed using today's date. And we create two random samples from control group and treated group. We put them into one data set. So this is what it look like. We assume this random variable, continuous random variable, as a rating score, and it's from control and treated groups. Okay. All right. So first we calculate the observed difference. Okay. And then we do permutation test. Here we're gonna do 10,000 permutations. That's a lot. Okay. And we create a numeric vector of 10,000 dimensions. And here's the main chunk of R codes for implementing the permutation test. So it's a for loop. First, we shuffle the group labels. So we just random permute the group labels. And then we just calculate the permuted differences and for the means, and that's the function. Okay. And then we extract the p-value, which is the mean of the permutation differences greater or equal than the absolute value of the observed differences. Okay. So in this case, the p-value is 0.2161. So if we use 0.05, so it's not significant different. The two distribution, the means of two distributions. Okay. So that's the whole process of the permutation test. Of course, if you want to do some visualization, we can put all the permuted differences into a data frame and using ggplot. You can see that a histogram is the distribution of all the permuted differences. The vertical line with the dashed dots, a dashed line, that's the observed differences, 2.76. And you can see it's far away from the center 0, but it's not really far away in the tails. So the p-value equal to 0.1. So it's not really reached the threshold for being significant. Okay. All right. So let's do another example for comparing linear regression models. So set a random seed, creating x's and y's, and here's the data. Let's take a look at the data set. Okay, so first let's compare the observed difference in slopes. Okay, so you calculate the slope, and then that's the observed difference. Okay. And then we do, so here we reduce the number of permutation to 5,000, and we create a numerical vector to store the permutations estimates, permutation differences, and we write a similar for loop, but this time we extract the permuted slope from the linear regression models. Okay, and then we print out the p-value here. The observed slope in group A is 3.13, and in group B is 1.47, and the difference is 1.66, and the p-value is 0. So it is significantly different. The slope of the two lines are significantly different in the two groups. Okay. So this is a more complicated example, and you notice that we reduce the number of permutation to 5,000, just to reduce the computation. Okay. But if you want to do more complicated models, then the computation will get more challenging. All right, I hope this video is helpful for you to learn a little bit more about permutation tests. Thank you.